Okay, hello and welcome to my foundation presentation. What I'm going to be going over first in the exercises is exercise about non-context free languages. It's 2.42 in the third edition of the book. And so essentially non-context free languages come into play because we started with finite languages, which can be written in terms of DFAs, and then we found what was not included in there, and which were regular languages, and then moving a step farther than that, we found that context-free languages were not inside of regular languages. And now we're trying to find the relationship between context-free languages and all the languages, which is going to be anything that's not in context-free languages, thus non-context-free languages. So we're going to prove that similarly to the way that we proved that CFLs are not in regular languages through a pumping lemma. The last one had 3 parts, which introduced the X, Y, and Z, where Y was a repeating loop, where if any accepting string touched Y, it would proved an idea that there would be a loop and things could happen n amount of times, so it wouldn't have to be finite or regular. So now we're going to take that a step farther and do a new pumping lemma into 5 parts: U, X, Y, V, and Z. That was a terrible alphabet, but so that lemma is important because the second and fourth parts, V and Y, can happen any amount of times, and that string is still going to be in the acceptance string, which I'm going to show how that works. So on the left side, I have just a quick little diagram about T being our input string, which can then be broken up into U, R, and Z. So U and Z are 2 of our 5 pumped lengths, and then R is going to be broken up even farther into either this first path here, V, R, Y, or into X. V, R, Y has to happen at least once, or else we won't have 2 of our 5 parts. So V, R, Y happens, and then after that it can be broken up into another V, R, Y, or X, and that shows the idea of a recursive aspect of our input string, and that's why V can go to the I and Y can go to the I, and X only happens once. So I do a few examples of that on the right side. I blew up 1 here on the left side, which is language 0 to the n, 1 to the n, 0 to the n, 1 to the n, where n is greater than 0, greater than or equal to 0. And this is going to be a non-context free language, and we're going to show why it can't be pumped. So I picked an arbitrary pumping length of 4. You could do a bunch of these. I think I did a few just to make sure that it couldn't actually be pumped. But so I'd take a pumping length of 4, which comes up 0 to the p, 1 to the p, 0 to the p, 1 to the p, so 0 to the 4th, and I write that out here. And this is not a way that you can pump this into 5 parts. I just wrote it it was a proof by contradiction, so you have to kind of exhaust a few methods. So you know that there's going to be the same amount of zeros and ones in V and Y, because looking at it, you know you're going to have to break this up into kind of 2 parts that can repeat any amount of times and still be an input string. So the closest I could even get to that was 0011 being a V and 0011 being a Y, and the rest of it being U and X and Z. And that doesn't work because V and Y, the zeros and ones aren't even going to the pumping length. It's about half of that, and if I was to repeat V and Y, it wouldn't lengthen the values of V and Y into the pumping length. It would just do 2 zeros, 2 ones, 2 zeros, 2 ones. So it doesn't work. There was a bunch of other ways that I tried to break it up, but none of them work, which is why it is a non-context free language. And so I do a few more examples, and so this one, 0 to the end, pound, 0 to the 2n, pound, 0 to the 3n, pound. You can tell right there that the pound, there's 2 pound signs that happen once, so those are both going to be 2 parts of your 5-part pumping length. You're going to have a U and an X be equal to those pound signs, and then so you've got V, Y, and Z, and there's no way for you to have V to the I and Y to the I happen so that they're going to be the an accepting string, because there's not even a pound sign anyways, so you know you won't have a repeating input string with just any amount of zeros being able to be accepted. So that one's not a context free language either. I go on further. C was very similar to the first example, and D was also pretty similar to that with the pound signs. I don't want to spend too much time on it, so I left the work up, but I didn't go over it. And so I found non-context-free languages to be a little bit difficult to prove because you had to do it via contradiction. But I thought it was a nice way to go over just how this R transition could be broken up into a recursive kind of way of having an input string. So I thought that was very helpful to be able to, once I was able to understand this diagram, it was a lot easier for me to do the pumping lemmas. And so that was a start to what comes next, which is Turing machines. So the next thing I want to talk about are Turing machines, and Turing machines are very similar to DFAs in the sense that they're able to take an input string and be able to determine whether or not that language is going to be accepted or rejected via a state diagram like the one on the left here and like a DFA. Turing machines add a lot of computational power because they introduce the control state, the head, and the tape. And the tape was something that gave me a bit of trouble, so I want to go over some of the exercises that help me to do that. The tape also introduces the idea of the blank spaces in the accept and reject state, which are part of the 7-tuple representation as opposed to DFA's 5-tuple representation. So the question 3.5 just helped clear up a few things about how to actually execute these Turing machines. The Turing machines can jump from left to right, and they can move any amount of spaces. So that being so this question, like A, can the Turing machine ever write a blank space on the table? That just helps me understand how in this state diagram that they are able to do that, and how each step, you see some blank spaces being written in here, how each step is executed. And can a Turing machine's head ever be in the same location twice? It's just a bounds check saying, you know, if I'm on the far left and I want to move left, I'll end up in the same spot because I need to read something to the right of me. And can a Turing machine never contain just a single state? It's just, it can't, because there's an accept and a reject state, so just inherently there can't be only one state. So I want to go over two of the well, I did two of the state diagram exercises. I'll just go over one. And so essentially what you do is you take the language like W, pound W, and W is any amount of zeros and ones, so if the input string is going to equal something in there. So we take a string like 10 pound 10, and we start at Q1, which is our start state, and we read something to the right of that, which is a 1. So we see this takes a 1, and it replaces that 1 with an X, which on the tape it writes an X, and it moves to the right. So, and we're in Q3. So now we're in Q3, we have our X, and we've moved to the right. Now Q3 reads in a 0, and it doesn't write anything, it just moves to the right. So now we're over here, X0, Q5, no, I'm sorry, Q3, pound 10. And now we read in that pound sign, move to the right one. Now we're in Q5, as it says up here. Q5 reads in an X, no, I'm sorry, Q5 reads in a 1, and puts in an X, and it moves to the left on the tape. So now we're in Q6, we're over here, and we have a pound sign on the right. We're going to keep moving left to Q7. The 0 on the right stays in Q7, moves to the left, reads an X, moves to the right, back to Q1. There we are. Q1 reads in a 0, puts in an X, moves to the right. We're in Q2. Now we're working this way, reading in a pound, moving to the right to Q4, and we're reading in an X from Q4. Yep. Moving to the right one, still in Q4, reading a 0, replacing that with an X. You can see this tape is being marked off with a bunch of X's here. XX pound Q6 XX. That reads in an X, moves to the left. Now we've got Q6 reading a pound, moves to the left, back to Q7, reads in an X, goes to the right, back to Q1, which reads in that pound. Now it's going to get to Q8, and it's got X's on the right of it. Keeps moving to the right until we're in Q8, and all we've got is blank spaces on the right, which brings us to our Q accept state, which this does accept. So that's an example of a Turing machine working. You can see like example C has 2 pound signs, so we get over to Q5, and this actually, the rest of this is not right, but Q5 can't read in a pound sign, so that goes to a rejecting state if it's unable to read in any of the input. So I thought the state diagram was a nice way of moving around the tape and being able to see a more detailed explanation of how that worked. So I got a lot out of these exercises, and I'm happy with both of them being up here. I think I may have learned the most from this exercise. So real quick, one thing that I wanted to add was the fact that there are different variations of Turing machines. There are Turing machines like multi-tape and non-deterministic Turing machines, similar to how a DFA has non-determinism eventually into an NFA, and that's just a design tool. So every multi-tape DFA that has multiple heads and non-deterministic Turing machines that have multiple heads or multiple tapes are all going to be able to be broken down into state diagrams like the one we just went over. So I didn't find any great problems in the book to describe that, but I thought that was an important concept that I didn't want to leave out. But so anyways, moving on to 4.3, which is the next example, which is about decidability. So Turing machines have the same computational power as a computer. So it's important to know that not every problem can be solved by a computer, and that's something that I had a little bit of a hard time grasping, and I thought this example was a pretty good way of describing a problem that doesn't seem like it can be solved, but actually can, and it is decidable. So you take this problem where all DFA is going to be equal to a DFA A, which is able to interpret the language of A, which is the language of everything. Sigma star is everything. So you need to see if all DFA is decidable. So what I struggled with here is I didn't know how to make a DFA that was going to be able to take everything as an input. So eventually, through reading the book, I realized that the way to do this is to make a DFA called A and have it go with its 5-tuple representation Q, sigma, delta. Q1 is the start state and F is the accepting states, where in this example F is just Qn. So I made a DFA, and that goes and is not really able to tell us much. So from there I made a complement, which is essentially the same thing except all the accepting states are reversed. So Q1 through Qn minus 1 are going to be accepting states, and then Qn is not going to be an accepting state. So through theorem 4.4, they're able to tell us that eDFA, which is an empty language, is going to be decidable, and I try to show here that that's decidable with the DFA A complement. So theorem 4.4 says essentially you start by marking your start state, and then every state that has a transition function from an accepting state, like from a marked state. So any state that has a transition from a marked state, you're also going to mark until you run out of states. So here we get Q1 is going to be an accepting state, Q2 and Q3. So if we're giving an empty language, then Q1 is going to be able to accept that language because there's nothing in it. So taking that, knowing that the complement of A is A complement, and that's able to accept nothing, we can then infer that the opposite of A complement, which is just A, is going to be able to accept the complement of the empty language, which is going to be sigma star. So I thought this was a really cool way of breaking down a problem that seems non-computational in terms of a computer, but is actually decidable. And I thought decidability through DFA is a very interesting concept that was able to help me understand the computational limits of a computer. So the last subject I wanted to touch on was uncountability and undecidability. So we went over an example of a language that was going to be decidable because it was able to be accepted by a Turing machine. So a language that is not even going to have the opportunity to be decided as an accept or reject state is one that has an infinite set as input. So in this example was able to give a good example of an uncountable sequence, because it's kind of hard to imagine a sequence of work that's going to be unsolvable. So this is an infinite binary sequence. It just says let B be a set of all infinite sequences over 0, 1. Show that it's uncountable using the diagonalization proof. So you take just any number of corresponding infinite binary sequences. You'll never get any repeating here because there's an infinite amount, and we have our x, which is keeping track of what is going to be the correspondence between this diagonal path here. Oh, okay. So we take the complement of each diagonal number, so you get a 0 here and a 1 there, 0, 0, 0, 0, and that's going to go on forever. So there's not going to be a matching n for this x, because this x goes on forever. So because that is part of the diagonalization proof, that is going to show us if there's no x that's going to match n, then this is not going to be a countable language. And if it's not a countable language, then it's not going to be a decidable language. So there are sets of work that are outside of the realm of Turing recognizable and decidable machines and languages, I mean. And so I thought that was an interesting closing argument, because it just shows that it gives us a somewhat concrete example of what computers are and aren't able to do, and I think that was one of the main points of this class. So I thought this was a cool example, and I definitely think I've learned a lot about what exactly, well, not what exactly, but what theoretically a computer can and can't do, and that's going to help me in my future endeavors. So that's it for this presentation, and thanks for listening.